Gradient boost algorithms represent some of the most powerful and popular predictive machine learning models used in industry. Now, in this video, I want to dive into how these algorithms actually work. Now, we're going to do this through a twofold process. First, I'm going to describe in detail what a gradient boost model is. And for this particular example, we're going to work with a gradient boost regressor, and we're going to describe how this model works from simple principles up until the actual mathematical definition for the algorithm. Next, we will jump into a Jupyter notebook where we will implement this algorithm in Python from scratch. And once we have this implementation, we will then verify that it is working, and we'll also check it up against other predictive machine learning models just to check and see how well our implementation is actually doing. So without any further delay, let's jump into the content of this video. So as its namesake would suggest, a gradient boost model is just a type of boosting ensemble. Now, an ensemble is a machine learning algorithm that combines a series of very simple models, and we term these simple models as weak learners. We combine these weak learners together in order to create a much more powerful estimator. Now, the original definition for the gradient boost algorithm, as it was defined in its original paper by Friedman in 2001, is that we could use any type of weak learner for this ensemble. However, in practice, what is normally used are decision trees. So let's take a look at what exactly is going on with each of these weak learners. In our case, a very simple decision tree. So here we can see a simple illustration for a decision tree with only one split. The split is based off of a variable called age and whether that age is greater than 30 or not. So here we can see a sample where we have an age of 42. It is greater than 30, so it's true, and it moves to the right-hand side of the tree. We take another sample, and the age is 18. It is false because it doesn't meet the condition of age being greater than 30. So it moves to the left-hand side of the tree. And this is essentially it. I'm avoiding the mathematical details here because it's not really relevant for this topic right now. But this should give you a very high-level understanding for how these decision trees are working. So then, how do we combine these very simple weak learners together in order to get a more powerful algorithm? Well, now we can look into what is meant by boosting and how does that work. So here we will see a very simple ensemble of 6 decision stumps. And the way boosting works is that we are operating in sequence. The first tree takes the raw data, generates predictions, we compute a residual on those predictions based on the true labels, and we pass that residual to the next tree. So each subsequent tree in our ensemble is learning from the mistakes of the previous trees. This is how, in the end, we are able to get a very powerful estimator that is constructed by joining together all these simple weak learners. So that is covering boosting, again, at a very high level. Now, one observation that was made is that this sequential approach to learning and to optimizing the performance of our model in this fashion is analogous to another algorithm that we may be familiar with, and that is gradient descent. So let's take a look at what gradient descent is doing. So with gradient descent, we're also approaching a problem, an optimization problem, in a sequential manner. Here we see a 2D surface that defines some type of loss function. Our red dot specifies an initial point, and we compute the gradient towards the local minimum. And using that gradient, we are able to approach this local minimum. We can see that here. The horizontal axes, that's R and gamma, can be thought of as model parameters, whereas the vertical axis is our loss function. So we can see that these two algorithms are in a strange way very similar to each other. Both boosting and gradient descent can be thought of as approaching an optimization problem through this sequential manner. And this is exactly what was noted in the late 90s, which led to the development of gradient boost. Now, gradient boost was defined by Friedman in his paper in 2001. What we're going to be working with here is one of the specific implementations of gradient boost. And so now we can look into what he defined for what he called LAD tree boost. Now let's look at the mathematical definition for this algorithm. We assume first that our weak learner is a decision tree, and that's what we see here defined mathematically, and our loss function is going to be the absolute value loss function. Those very simple values. Now in his paper, we're following algorithm 3. And so we start off by initializing our estimator to be equal to the median of the training labels. We then iterate through all m weak learners in our ensemble. The next step is to compute the gradients. The gradients are equal to the sign between our training labels, yn. We subtract out from this the value of our ensemble, which is m-1. And we do this for all samples in our training data, which is n. We then fit a decision tree to the data that we have. So that is, it's going to be fitted on our set of input predictor features and the gradients that we just computed. And we do this over the entire data set, so we get a set of terminal regions for this particular weak learner. So here we're just training the weak learner in our model. The next step then is to compute these gammas. This is gamma subscript jm, and these are evaluated as the median of this difference, the difference between the training label and the value of the ensemble at m-1. So that's all we do to evaluate these gammas. And once we have this, then we're able to update our ensemble. And the update rule is what we have at the end, and that is equal to em minus 1, which is the current value of the ensemble. And we add to it these gamma parameters that we just computed, and we evaluate it based on the terminal regions for the decision tree that we computed as our weak learner. So the I here is just it's the identity matrix. So basically it's going to be equal to 1 whenever our sample at this particular point is within one of the terminal regions. And then we basically fetch out the relevant gamma for that terminal region, and we add it accordingly to our ensemble value. So now let's jump into a Jupyter Notebook where we will flesh out these ideas that we've just covered and make it a bit more tangible by actually implementing this algorithm. So now we're in a Jupyter Notebook, and before we get started, just note that this notebook is available on my GitHub, and I've provided a link to this notebook in the description below. So let's start by importing all the packages that we will need later on. So that's just in this first cell. And now, the next thing that we're going to do is define our implementation. Now, our gradient boost tree regressor is going to be encapsulated in this class. So the first two functions that we have here are just an initializer and a destructor. For the initializer, the user is able to define the size of the ensemble that we're going to have. So that's defined by this n elements. It initializes to 100. And then we can also set the maximum depth for the constituent weak learners in our ensemble. And it initializes to just have a maximum depth of 1. So that's what's going on with our initializer and destructor. The next function we have here is a private function, And we use this to compute the gamma. If you remember from our algorithm definition, the gammas come out from the second last step in the algorithm. And the gammas are what we use to update our ensemble at each step during the training phase. So what we do here is we take in as arguments an array of the predicted values for our data for each sample. And we also take in the true labels, that's this Y train. And we also pass in this array called E. And E is just the value of the ensemble at the step that was determined at the previous step. So the first thing that we do here is we just initialize our variables. So what we're going to initialize here is just this array called gamma jm. Let's hold our gammas, and these are just going to be set to 0. And so then we also compute this regions array, and the regions are just the set of unique values that were determined by the weak learner. So we just compute the set of unique values coming from our predictions input. So that's YP. I'm also going to define this dictionary, also called gamma. And the distinction between gamma and gamma JM is something that I will get into just a little bit. For now, just follow along. And so now what we're going to do is cycle through all the different regions that were found by our weak learner. We identify an index for each of the regions. So in this particular region, we basically see where it's equal to the prediction value, and we keep note of that. And we use this index to isolate out the relevant points of our ensemble array and also our training labels. That's what we do here. And now, having that information, we are going to compute the gamma, and that's what we saw defined in our algorithm. That was the second last step, was we just compute the median of this difference between the training labels and our ensemble values. So that's all we do here. And now we're going to store this value, gamma r, within this array called gamma jm, and we store it on the relevant elements of this array. So you notice that here we use the same index as we used previously, and we just store the gamma r values there. And I'm also going to store gamma r in this dictionary. But in this case, the dictionary uses the region as a key, and then we just set the value gamma r to this key. And so that's all we're doing. We then append the array of regions to this internal variable called regions, and then we're going to return both the gamma objects. Now, why do we have two coming out? Well, it turns out that just for formatting reasons, the first gamma array is what we will use when training the ensemble. And so this is just a convenient form. It's just coming in as an array. And we're going to use this when training. We can just directly apply it. However, for predictions, we need something a bit different. And so the gamma dictionary is what we're going to use when we have to generate predictions off of this ensemble. So that's just the reason of this difference. Now let's move on to the fit method. So that's what we see here. And we're going to use this to build our ensemble. So fit takes in the set of predictive features, that's xtrain, and we also take in an array of our labels, and that's ytrain. Now, the first thing we do is that we reinitialize our internal variables. We have f, which is going to contain all the weak learners for ensemble. We have the regions, and this is the terminal regions that are identified for each weak learner. We also have an array of model weights, and then I'm also going to be recording the mean loss, and this is just so we can look at it later to verify that the model is training correctly. So once we have that, we start off with our algorithm. If you remember, we start off by computing the median of the training labels. That was the first step, and we set that to this value called E0. And we basically assign an internal variable to keep a copy of E0, and then we format it to convert it from just a scalar to an array value. And now we're going to loop over all the elements of our ensemble. So this was the second step of the algorithm. We first compute the loss, the current loss at this step. So this is just the mean absolute error loss that we have here. And I'm just recording this again just to see how our model is doing. The next thing that we do is we compute the gradients of our loss function. So this is now the next step that we saw defined in the algorithm. And the gradient for this loss function is just going to be equal to the sign of this difference. It is the sign of the training label and the value of the ensemble at this point in time. So that's all we're doing. We then go to the next step in our algorithm, which is to train or to define first our weak learner and then train it. We're training it on the input predictor features that we see here and the gradients, which is G. And now we generate predictions on the training data. That's what we got with YP for this weak learner. And we feed this YP into our compute gammas function, which is what we just looked at a moment ago. And so here we compute our gammas, and that is then the second last step in our algorithm is just to compute the gammas. And then the final step is to update our ensemble. And that is just by adding the gamma JM to E. So that's just updating the ensemble value, and then we keep iterating over all the elements of our ensemble. Now we store here, you'll notice at the end, we store each of the weak learners, and we're going to store the gamma value, the gamma, the second output from the compute gammas function. So we keep track of that here. And that's it. That's the whole training procedure. That's how we're going to implement it. Now, let's take a peek at how we generate predictions from a model that has already been trained. So in this case, our input to this function is just going to be the set of input predictor features. And now we initialize the output in a way that's analogous to what we did previously. We basically use this E0 value. This is the initial value that we set previously. And we basically define an array with all these values in it. So it has the same number of samples as the input data that is provided, and they all have the same value, which is E0. We then cycle through each of the weak learners, and we do that by cycling through these three arrays simultaneously, which is F, which is the array of weak learners. We cycle through the array of gammas, which has the same length, and the set of regions, which also, again, has the same length. So we iterate through each one at a time. We generate predictions on the test data now using our weak learner. We do this by iterating through all the regions that were identified during the training phase, and then we match up our predictions with each of the regions. We set an index according to that, and then we update the relevant elements in our prediction array with the gamma values. And here you can see this is the dictionary now. This is a dictionary form of gamma where the key is just the region. So this is how we're doing this. This should look very familiar to the update rule that we were using for during the training phase. And so this is all we do. This is we cycle through all of this, and then we output the predictions. And that's how generating predictions works. Now the last two functions here are pretty simple. We have a function to return the loss. I also defined a function here to return the model input parameters, which is the number of elements and maximum depth. So that's it. That's the whole implementation. Let's run the cell. And now let's actually see how well it performs on a real data set. So here I'm going to be using the diabetes data set that is available from scikit-learn. I've defined in the notebook, I've kept some notes of what the input predictor features are, but we're not going to cover that in any detail right now. Let's just go ahead and load in the data. And now let's take a peek at how well the model is doing, how well our implementation is. And we're going to do that by training it on this data. So we want to see how the model is working. I'm going to record the loss, but I'm also going to do this a number of times. And for each step, so you can see that here in the different cells, I'm going to update the maximum depth of our weak learner. So you can see here, I just use the default value. I don't specify it in the first case, so it's just going to be 1. And then I set it to 2, then 3, and then 4. I record the loss for each, and then we're going to see what the output looks like. So let's just run through these cells. We can see that the training happens pretty quick. Now let's plot the results. So right away, this looks pretty neat. We can see right off the bat that our implementation is working. We see results that we'd expect. So the vertical axis shows the loss value. This is the mean absolute error. And the horizontal axis is the number of component trees. So if we look back up, we can see that each of these ensembles has 100 elements. So that's why the horizontal axis goes from 0 to 100. As we iterate through the ensemble, the loss declines. So it first declines very steeply here initially, and then kind of plateaus out. And this is what we would expect from the model itself. So that's already a good sign. The next thing that we notice is that as the maximum depth gets larger, the loss actually gets lower. And again, this is what we would expect, because as maximum depth gets bigger, each of our weak learners actually becomes more powerful. It's able to generate better predictions. So overall, our ensemble is going to operate better. So this is all pretty good. It's pretty consistent with what we would expect. But how well will our model work against other implementations? So let's go through that now. The first thing I'm going to do is I'll look at our implementation that we did. So here I'm going to use gradient boost tree regressor again. And I'm going to take a look at it if we have a somewhat smaller model. So I'm just going to set the n elements to be equal to 20. And our maximum depth will again be at 1. We're going to do a cross-validation analysis on it with 10 folds. And here we can see what the average results are for the mean squared error and the mean absolute error. So we see this. Now, how does this compare against, say, the scikit-learn implementation for a gradient boosting regressor? Well, let's take a peek. So we can import that model, and we can use the exact same setup to measure its performance. So okay, here we see the results, and it's pretty similar to what we got with our own implementation. So that's a pretty neat vindication that we've done our job pretty well. So that's already a great result. When I first saw that, that was really nice to see. Let's compare it now with a few other different models. So let's just use a decision stump. And this just is a decision tree with, again, just a depth of 1. Unsurprisingly, its performance is not that great. Let's compare it with a random forest. A random forest does a lot better than the decision stump, but it's not as good as what we saw with the gradient boost. So the final algorithm I want to compare it against is AdaBoost. And AdaBoost is an earlier version of boosting. And we're just going to use the scikit-learn implementation here to see how well it performs. So here we can see AdaBoost does a bit better than the random forest, but still not as well as our gradient boost ensembles. So for a previous run, you can see here I've tabulated the results. And it's pretty apparent that the gradient boost approach is giving us the best results. Afterwards, AdaBoost is the next contender, followed by the random forest. And then it's not too surprising that the decision stump really didn't do that great at all. This should just illustrate why gradient boost models are so popular for predictive tasks. It's just that their performance in practice is a lot better than the competition that is out there. So this concludes the video. If you want to take a closer look at the mathematics and how we derive the algorithm that we've implemented here, you can take a look at a blog article that I wrote a couple of years ago on this topic. I've attached a link to this blog article in the description below. Now, I hope you enjoyed this walkthrough of the gradient boost algorithm that we've done. Certainly, I learned quite a lot by implementing this myself and testing it out and verifying that the implementation actually works. I thought it was pretty neat. And it gives a lot of insight for one of the most powerful algorithms out there in industry. So I've personally used Gradient Boost quite a lot in various different jobs, and it's likely that you would also encounter this if you're working on a predictive problem. So I hope you got some value out of this. If you did, please like, share, and consider subscribing to the channel. Your support is greatly appreciated. Have a great day, and I'll see you in the next video.